Okay, so welcome back to another live session with me, Joe. In this session, we're going to be looking at series. Okay, so I've set up there's 4 topics that we're going to go through, and they're all once again based upon the edXL curriculum. So we're going to be looking at the arithmetic series, the geometric series, and those are the 2 main ones. And then we're going to look at segment notation, and then finally round off with recurrence relations. Okay, so first things first. Let's start off with the arithmetic series. So the arithmetic series, or rather sequence, is when we have something like, for example, 2, 5, 8, 2, 5, 8, 11, 14. You can see here, this sequence is increasing by a value of 3 each time. Okay. So this 3, we call it a common difference. So you can see here, I've written D out as the common difference. That just represents the difference in which we're increasing, or sometimes it can be decreasing. So for example, if I had a series like 17, 12, 7, 2, minus 3, like this, you can see now we are going down by -5 each time. So in which case, that means that we are, in this case, decreasing by -5. And so our common difference, our D value, is going to be -5 in this example. Okay, so that's our D. Our A value, which we also need to learn, is known as U1, sometimes defined as U1. And this just represents the first term of the sequence, okay? So first term of the sequence. So in our case here, our A term will be 2 in this first example here. And the second example, our A term will be 17, like so, like this. Okay, so those are the 2 main things we do need to know about the arithmetic series. Right, so if we do know that, we can actually we can form a formula called the nth formula. And basically it's shown here, un like this, right? And un just represents a way of finding the nth term of any arithmetic series, okay? And that's just a plus n minus 1 d, like so. So if we go back to the example, we can say that if we had that 2, let's go for 2, 7, 12, 17, 22, 27, 32, like this. Let's find that A. So our first term A will be 2. Our common difference, we're going up by 5 each time, right? So D would be 5. So once we've identified our A and D terms, what we need to do is just plug it into unth term formula like this. So for this certain arithmetic series, un would be equal to A is 2 plus n minus 1 times 5, like so. Okay, so this is going to be our unth formula, which you can also simplify if you want. So it'd be 2 plus 5n minus 5. So this will be 5n minus 3, like this. Un is going to be 5n minus 3. Okay. So this is, as I said, this allows us to find any term within the arithmetic series. So we can look at an example. So let's say, if you look at this term here, this was 1, 2, 3, 4, 5, 6. This is the 7th term, right? U7. So let's just make sure that our nth term formula works, okay? So if n is 7, U7, we just have to plug it in. It's going to be 5 times 7 minus 3, 35 minus 3, which is 32. And yes, we get the same value of 32. So we know our nth term formula is correct. Okay, so that's the nth term formula. Now, for the arithmetic series, we can also find the sum, okay? And sum of the arithmetic sequence, we define as Sn. Now, the difference between the word sequence and series, you might see that now and then, is that a sequence is just representing just like the terms within the series. If they said arithmetic series, it just means the whole sum, okay? So that's the difference between sequence and series. So the sum formula, you can see here is n over 2, 2a plus n minus 1d. And once again, this is for an arithmetic series. In the edXL curriculum, you do need to know how to prove this one as well. So let's go ahead and try and prove it. So first of all, Sn. As we said, it's a sum of all the terms, right? So if we write it in the generic terms in terms of a and d, well, the first term will be a. The second term will be a plus d, right? And let's just write one more. So plus a plus 2d, like so. So these are the first 3 terms. And I'm also going to write the last 3 terms as well. So the last term would be, let's just write the last 2 terms. So a plus n minus 2d. The last term would be a plus n minus 1d, like this. Okay, so these are all the terms that we're summing up to get our Sn. Now I'm going to rewrite Sn once again, but I'm going to write it from largest to smallest, so back to front basically. So the largest one will be a plus n minus 1d, plus the second largest will be a plus n minus 2d, and then we can go plus plus plus, and then the last term, let's just write the last two terms of a plus d, and then plus a like this, okay? So I've just rewritten out the sum equations or the sums of the arithmetic series just back to front. Now what we're going to do is actually just now sum these two together, so add them together. Right, if I add them together, we get Sn plus Sn, so I get two lots of Sn on the left-hand side like this. Now the right-hand side, well, you can see that the right-hand side, if I sum these two terms together here, I get a plus a, so 2a plus n minus 1d like that, okay? Now, if I add these two terms together as well, what you get is actually the same term, this 2a plus n minus 1d. So we get the same term here. And what this means is essentially that we just get n terms or n amounts of this 2a plus n minus 1d like this. And so because I want Sn, I just simply have to divide by 2. So I get n over 2, 2a plus n minus 1d. And this is how we get or create the sum equation for an arithmetic series. You can see here, there's actually two different versions of the sum equation. So we just proved the first one here. You also need to be able to prove the second one here as well. This Sn is n over 2a plus l. And that's simply from this term we got here, okay? So what I'm going to do is I'm going to say Sn is equal to n over 2. And then this a, I'm going to split up into a plus n minus 1 d like so. And hopefully what you realize is this term here, there's a plus n minus 1d. It's actually the last term of an arithmetic series. So we can replace it with L. So Sn is equal to n over 2, a plus L, where L is the last term within the arithmetic series, okay? So this is how you go ahead and prove these two equations. As I said, you need to know how to prove them both, okay? So make sure you understand what we just did, how we went about proving it, and just practice it yourself, try to memorize it yourself. So basically, that's all the theory you need to know about the arithmetic sequence and the series. So let's go ahead and try some examples. So you can see here, let's look at this example here. So we have an arithmetic progression and it has first terms a and common difference d. The sum of the first 50 terms is 5,200. Another arithmetic progression also has his first term a. The progression has common difference 3d and its 20th term is 234. Find the values of a and d. So we're given two different arithmetic progressions or arithmetic series. So what we're going to do is look at each individual one. So let's look at the first one. Okay, so we have an arithmetic progression, has first term a and common difference d. And then the sum of the first 50 terms is 5,200. So what we know is that S50 is going to be 5,200. So let's just create a formula for that. So we can have 5,200 is equal to, I've written out the formulas here. So it's the sum equation here. It's going to be n over 2, n being 50, right? So 50 over 2 times by 2a, a we don't know, plus n is 50 once again, minus 1 times d, which we also do not know as well. So this is going to be our first equation. Let's slightly simplify this a bit if we could. So I'm going to divide by 5,200 by 25. So I get 208 is equal to 2a plus 49d. So let's call this one equation number 1. Okay. Right. Now looking at the second equation or second sequence, which says the progression has a common another arithmetic progression also has first term a. This progression has a common difference of 3d and its 20th term is 234. Right, so we can create another formula from here. Remember, its note is not the sum, okay? It's saying its 20th term. So we should be using the un equation. We shouldn't be using the sum equation in this example. So they've told us that u20 is going to be equal to 234. So let's go ahead and create an equation for that. So we can say 234 using the nth term equation, right? un is a plus n minus 1d is equal to a plus n. So a plus n, n being 20, 20 minus 1 times. Now the common difference in this case is going to be 3d, because they said it's 3d, right? Not d, so times 3d. So this is where we get our second equation. So let's simplify this a bit. So we get 234 is equal to a plus 57d. Okay, so we get equation number 2. And so what we can do now is, because we have two equations and two unknowns, we can now go ahead and do simultaneous equations to try and find what our a and d values are. So trying to do that. So let's go 208 is equal to 2a plus 49d. And I'm going to times the second equation by 2. So I get 2a plus 114d is equal to 468. Let's go ahead and subtract. And so we get minus 65d on the right hand side and minus 260 on the left hand side. And so d comes out to be equal to 4 like this. Once we found d, then we can just substitute it into either of the two equations here or here and to find our a value, okay? So which you guys can do, okay? So this is just making sure you understand which formula to use to create these two equations. All right, let's try another example. So let's try this one here. So we have the fifth term of an arithmetic series is 33, the 10th term is 68, the sum of the first n terms is 2,225. Show that this equation is such. Okay, so we're given the sum of the first n terms. So let's write it as Sn here. S in this case, n is equal to n over 2 times 2a. Now the first 2a plus n minus 1d. Okay, so that's the initial equation. Well, that's the generic formula, and this is going to be equal to 2,225. Right, so we don't know a or d as well. So in this case, we have to find it first. So it told us that the fifth term is 33. So we know that u5 is equal to 33 like this. So we can say that a plus n minus 1, so 5 minus 1d is equal to 33. Okay. Okay, the second thing is they told us a 10th term, u10 is equal to 68. So we can say that a plus 10 minus 1 d once again is going to be equal to 68. So you can see what we're doing here. We're creating two formulas and we're going to use simultaneous equations once again. So let's go for a plus 4d is 33 and a plus 9d is equal to 68. Let's go ahead and subtract. Minus 5d, what do we have there? We have minus 35. So d is going to be equal to 7. And then plugging it back into either one, let's plug into here. So a plus 4 times 7 is equal to 33. 28, so a is 5. So we found the a values and our d values here. This is needed, right? Because we need to plug it in into this generic formula here and here, okay? So let's go ahead and do that. So if I do that, I get that 2,225 is equal to still n over 2 times 2a, so 2 times 5, plus n minus 1 times by d, which is going to be equal to 7, like this. And if you go ahead and expand this, then you do get what they want you to get here, the 7n squared. I'm not going to do it, but it's just simply expansion, basically. Right. So if we do that, then we can go ahead and do part B. It says, hence find the value of n, okay? So n is just basically, because we formed this quadratic equation at the beginning, we can just factorize this one here, right? So 7n squared plus 3n minus 4,450 is equal to 0. So we can go ahead and factorize this. And if we do, we get 7n plus 178 and n minus 25 is equal to 0, which means that n is either minus 178 over 7 or n is going to be equal to 25 like this. So we get two values of n. However, we have to make sure that we understand what n is, right? N is actually the number of terms within this arithmetic series, meaning that n can't be a negative value and it can't be a non-integer. It has to be a positive integer value, which means this solution here cannot be a solution. So the only solution is going to be when n is equal to 25. This is a common question that they do give you just to make sure that you understand what n is going to be and making sure that you guys give the correct answer. All right. So that's more like basic practicing the arithmetic series. We can actually, in the exam, they'd give it to you based upon like some modeling questions. So they base a model based on an arithmetic series. And so it's the same thing, it's just making sure you understand which equation to use and which formula to use as well. So we have this is the past paper exam question, which we're going to go through. So we have Jill, who gave money to a charity over a 20-year period from year 1 to year 20 inclusive. She gave £150 in year 1, 160 in year 2, 170 in year 3, and so on and so on. So that the amounts of money that she gives each year formed an arithmetic sequence. Find the amount of money she gave in year 10. So you can see that what we're counting is the amount of money she gives to charity. And you can see that it increases by, if it's from 150, 160, 170, it increases by £10 each year. So what we can deduce straight away is that A is the first year we give money, which is 150, and D, which is the common difference, how much it increases by, in this case, 10. And so if I want to find the 10th year, I need to find the UN equation. The UN is equal to 150 plus n minus 1 times 10. And so they want the 10th year one, so I can just say U10 is equal to 150 plus 10 minus 1 times 10 like this, which gives us, which tells us that Jill gives to charity £240 in her 10th year. Okay, B, it says calculate the total amount of money she gives over the 20-year period. So understanding the question, it means basically the sum of the 20 years she gives. So if it's a sum, then we use the SN equation, right? So it's 20 years, so N will be 20, so S20. It's going to be N over 2, so it's 20 over 2 times by 2A. So A is still the same, 150 plus 20 minus 1 times the difference, common difference of 10, like so. And then if you work this out, it gives that Jill gives to charity £4,900 over a 20-year period. Right. So we've got now more information. So it says Kevin also gives money to charity over the same 20-year period. He gave £8 in year 1, and the amount of money he gave each year increased, forming an arithmetic sequence with a common difference of £30. The total amount of money that Kevin gave over the 20-year period was twice the total amount of money Jill gave. Calculate the value of A. Right, so we've got a new arithmetic sequence representing Kevin's model. Okay, so for Kevin's model, his initial amount he gave was A, which is capital A like this, and his common difference was increasing by £30 each year. So if I want to work out the sum for S20, simple again. So it's going to be 20 over 2 times 2A, but in this case, 2 capital A, that's the initial amount that we're trying to find, plus n minus 1, 20 minus 1 times by D, which is 30 like this. Now, the information that's given us is that the total amount that Kevin gave was over the 20-year period was twice what Jill gave. So this has to be equal to 2 times what Jill gave, which we found in the previous question, which was 4,900, like so. We've formed a formula. Now we can go ahead and solve for A. So what do we have here? We have 2A plus 570 is equal to 980. 2A is 410, so A is going to be equal to £205. That's the initial amount Kevin used to give in the very beginning. So it's just basically creating two different arithmetic formulas and then linking them together by the extra information that we are given in the question. Okay, so that's really it for the arithmetic sequence and series. We're going to change and go ahead and look at the geometric ones. So the geometric sequence or geometric series first is when we have an example of like maybe 2, 4, 8, 16, 16, 32, 64 like this, or even like 1,100, 10, 1, 1 over 10, 1 over 100 like so. What you notice now is the sequence is increasing or decreasing by the same multiple. Okay, so in this case, we're going multiplying by 2 each case to get the next term within the sequence. In this bottom one, we are dividing by 10 in each case to get the next term within the sequence. But what we're multiplying and dividing is also the same for each one. If this is the case, then we can define it as a geometric sequence, okay? And for a geometric sequence, the important letters to note are, first of all, A, which is the same thing as the arithmetic one. It just represents U1, the first term within the geometric sequence, and R, which in this case represents the common ratio, i.e. what we are multiplying or dividing each term to get the next term. So essentially for this example here, our a would be just 2 and our r would also be just 2 like this. For the bottom one, our a would be 1000, that's what we initially started off by, and r would be 1 over 10 like so. So that's how you identify each one. Okay, so that's the un. So once again, if we do know that, then we can create the un equation. So un is just equal to a times r to the power of n minus 1. This is the unth equation for a geometric sequence, which you guys have to also remember. The sum equation is here. You can see this here, summation equation. And once again, you do need to know how to prove this one as well. So let's go ahead and try and prove this one. So Sn. Once again, I'm going to write it out in terms of a and r, the generic form. So the first term was a, plus the second term, it will be a times r, plus the third term will be ar squared. And then if you go ahead, the second to last one will be arn minus 2. And the last term will be ar to the power of n minus 1. That's what we're summing up. Now, what I'm going to do is, rather than write Sn again and write it back to front like we did for the arithmetic one, what I'm going to do now is just multiply it by an r value. So in this case, it's going to be r to the power of Sn like so. In which case, I can multiply each term by r. So if I multiply a by r, it's going to be ar, right? So I'm going to write it actually under here. So it's ar like so. Multiplying this by r will give me ar squared. So I'm going to write it under here like so and so. And you can see what I'm doing here, right? Ar cubed and so on. This term, if I multiply it by r, will be arn minus 1, plus this term multiplied by r will be ar to the power of n, like so. Now, what we're going to do is actually subtract. So I'm going to do Sn minus r to the power of rsn like this, okay? And so the reason why I'm doing this is if you look at what the terms here, if I subtract it, what actually happens is these two terms will cancel each other out, because I'm doing ar minus ar. So will these two, and these two, and these two, and so on. And what we're actually left with is just the first term a, so a, subtracting the last term, this term here, ar to the power of n like this. That's all we're left when we subtract one from the other. Now, factorizing, so I can take Sn out, so Sn 1 minus r like so, and taking a out, a 1 minus r to the n, and dividing by that to leave Sn is how we prove the sum equation for a geometric series. Okay. So once again, you do need to know how to prove this one, so go ahead and actually practice proving it without looking at any of the examples, just to make sure you guys know how to do it. Okay, there's actually one more equation that you do need to know for a geometric one. So for both parametric and geometric, you need to know the nth term equation and the sum equation. But for the geometric one, there's actually one more, and that's the sum to infinity equation. Okay, sum to infinity. And it's denoted by this symbol here, s to the power, s like this, s infinity. Right. And this is going to be just simply a over 1 minus r. You might have seen this one before. So when do we use this? Well, we can't use this for every, this is for geometric, by the way, and you can't use this for every geometric series. It only works for a converging geometric series. And converging is defined when the r value or the magnitude of the r value is less than 1. An example would be this. For example, if we had like, let's just do 2, 4, like we did before, 2, 4, 8, 16, 32, 64, like so. And the previous example was 1100, 10, 1, 1 over 10, 1 over 100. Remember, our r value here was 2 and our r value here was 1 over 10, okay? So this sum to infinity formula would only work for this second formula here, or second equation here. The reason being is if we were to look at the terms for the first one, they are increasing in value as we go along, okay? So they're getting bigger, bigger, and bigger. And basically it's diverging away. And so if I try to find the the largest value, it will start getting bigger and bigger. So we can't actually find for like n infinity, and its infinity is going to be such a big value that it doesn't reduce to one single point. Whereas if I look at the second one, the terms themselves as we go along are getting smaller and smaller and smaller. So eventually when we get to the infinitive term, it will reduce to a single point. So we can't find the sum to this equation. So this equation here, we can't use it for this one. We can only use it for this second one because the R value or the magnitude of the R value is less than 1. So to make sure that R value, if its R is bigger than 1, just make sure you understand that we can't use this sum to infinity 1. Anyway, once we've identified that, what we can say is that as n tends to infinity, r to the power of n, it tends to 0. And remember the sum equation, right? Sn is a1 minus r to the power of n over 1 minus r. If r to the power of n tends to 0, this 1 minus r to the n will tend to 1, leaving just sum to infinity as a over 1 minus r like this. This proof you don't have to know, okay? So this what we just did, the tending thing you don't have to know. You just have to understand when we can go ahead and use it. Okay, so we can look at some examples, okay? So this one here. So the second term of a geometric series is 3.75 and the sum to infinity is 20. Find the two possible values of r, okay? So we're given information, let's go ahead and form some formulas. So second term is u2, and that's going to be equal to, if we write it in terms of a and r, right? So it's going to be ar, just ar like this. And that's going to be equal to 3.75, like so. The sum to infinity, s infinity, is going to be equal to a over 1 minus r, and that's just equal to 20. Right, so we need to find r, right? So let's go ahead and substitute for r. So from here, I can say that a is going to be equal to 3.75 over r, which I'm going to substitute into here. So we get 3.75 over r over 1 minus r is equal to 20, like so. Let's go ahead and expand it. So 3.75 is over r is equal to 20 minus 20r. Multiplying by r, we get 3.75 is equal to 20r minus 20r squared. And what you essentially get is a quadratic formula again. So you get a lot of quadratic formulas when we're dealing with both sequences. And so you're going to have to go ahead and factorize this one. I think I've done it before earlier. So if you do this, we get an r value of both 1 over 4 and 3 over 4 like this, okay? So this factorizing part you guys know how to do. Okay, so find the corresponding two possible values of a. Well, we found the r values, right? 1 over 4 and 3 over 4. So to find a, we can just simply substitute it into this equation here, okay? So that's fairly simple. And if you do that, I'm going to just tell you guys what you get. So you get a is going to be equal to 15 if you substitute 1 over 4, or 5 if you substitute 3 over 4, okay? Now, the part C is the more important part. So if we look at part C, it says, given that r takes the larger of the two possible values, find the smallest value of n for which Sn is larger than 19. So r is a large one, so it's 3 over 4. So r is 3 over 4. So r is 3 over 4, and our a value associated with the r was 5, okay? And so they're saying find the value of n when it gets larger than 19, okay? So once again, let's go ahead and create the formula. So the Sn formula was a 1 minus 3 over 4 to the power of n over 1 minus 3 over 4 like this. And that's going to be equal, greater than 19 like so. Kagwan said, what country is this? It's 8 p.m. for me now. We're actually in the UK, so yeah, it's 2:30 now UK time. Well, anyway, it's so this is the Sn formula, or S specific, and we're trying to find n. So what we can do is simply just rearrange this, okay? So if I do that, I get 1 minus 3 over 4 to the power of n is larger than minus 9, or actually smaller than minus 19 over 20. Okay. The reason why I change the inequality is because remember this is a negative value, right? Oh, sorry. It's still larger than. I'll just write it out again. So 1 minus 3 over 4 to the power of n is larger than minus 19 over 20. Okay, let's rearrange. So we get 1 over 20 is going to be larger than 3 over 4n. Now, to get this n value right, we have to use logs. So that essentially, when we are using geometric series or when we deal with geometric equations, we use logs a lot, okay? So to make sure you are comfortable with logs. So if I do use logs, I get log 1 over 20 is larger than n log, using the rules 3 over 4. And so because I want n, right? So I can get n is going to be equal to log 120, 1 over 20 over log 3 over 4. Now, log 3 over 4 is a negative number, so make sure you just change the inequality sign around like this. So n is going to be larger than this. And just simply plug it into the form calculator. So n has to be larger than 10.41. And remember, n is a number of terms, right? And it has to be a positive integer. So the next larger term will be n is 11, like this. So the sum of when it enters this geometric series is greater than 19 will be the 11th term, like that. Right, so that's basically practicing using the geometric series. Now we can, like the arithmetic one, we can go ahead and apply it to models, okay? In fact, the geometric model series is actually more common in use for real-life models because it allows us to show increases or decreases by a certain percentage. But percentage differences is a much more applicable way of describing models. So if you look at this here, we have a competitor is running a 20-kilometer race. She runs each of the first 4 kilometers at a steady pace of 6 minutes per kilometer. After the first 4 kilometers, she begins to slow down. In order to estimate her finishing time, the time that she will take to complete each subsequent kilometer is modeled to be 5% greater than the time that she took to complete the previous kilometer. Using the model, show that her time to run the first 6 kilometers is estimated to be this value here. Right, so we got a lot of information, okay? So first, let's break it down. So first things first, looking at the first paragraph, it says, she runs each of the first 4 kilometers at a steady pace of 6 minutes per kilometer. So the time it takes for the first 4 doesn't change. So we can straight away, we can say that it's going to be 6 plus 6. Just write it down here. 6 plus 6 plus 6 plus 6. Just 24, right? It's the first 4 kilometers. Now, after that, she starts to slow down. And it says that she slows down by, or her time is going to increase by 5%. Oh, yeah, 5% each time. So that tells us that our R value, the common ratio, is going to be equal to, this is where to be careful, okay? So the common ratio is not 5, because it's a percentage. It's actually 1.05 like this, okay? Because we are increasing the time. Now, if they were to say it decreases it, what you have to use is R is going to be equal to 0.95 like this, but it's going to decrease the time. So make sure you know how to convert percentages into R values, okay? So we're going to look at when R is 1.05. And so it says, show that her time to run her first kilometers is estimated to be this. So that first, 6 kilometers. So the fifth kilometer will be 6 times 1.05, and the sixth kilometer will be 6 times 1.05 squared, like so. Okay, so let's go ahead and plug this into a calculator. Okay, and so what I get is 36.915, okay, minutes, okay? And remember, because we have to change it into seconds, if you do change this into seconds, then you do get the value of 55 seconds, the one they asked us, okay? Right, so that's part A. Part B, show that her estimated time in minutes to run, I'll just get rid of this. Show that her estimated time in minutes to run the half kilometer is given by this here. Okay, so 6 times r 1.05 to the power of r minus 4. Right, so let's write out what her time was going to take, right? So first was 6. 6. The second one was 6 as well. So there's 4 sixes, right? And then the first term was 6 times 1.05, and then 6 times 1. So this is when we started using the geometric series sequence. So it's 1.05 squared and so, okay? And so they're saying find the half kilometer from 5 to 20. So it's from here up to the 20th term, right? So that's why we get 6 times 1.05. Now in this case, it was 1, 2, that was right. But the R value, it starts from when R is here, right? So this is when R is 1, this is when R is 2, and so on. And so therefore, because there's been 4 R's already, that's where the R minus 4 comes from, okay? All right. In the final part, using this model, estimate the total time in minutes and seconds that she would take to complete the race, okay? So the total time being, because we've modeled it out, is going to be these 24 minutes here, plus the total time up to here, right? So it's very similar to what we did in part A, because we looked at the first 6 minutes. Now we're looking for the whole 20 kilometers. So from this equation here, we need to create or use the summation formula just to make sure, just to get the sum of each one, okay? Right, so sum. Now it's very important that you understand what our A value is, okay? So this is from kilometer number 5, and we're going all the way to the 20th kilometer. Okay, so our A value, we're going to start by using this 6 times 1.05 like this. It's not going to be 6, because this 6 here is not part of the geometric series. It's not the first term. We can think of the first term as this 6 times 1.05. Our common ratio R is still going to be 1.05 like so, okay? And our N, well, we're going from the 20 kilometers to 5, so our N is going to be equal to 15, okay? And so we got our A, R, and N values, and we can just simply go ahead and plug it in, okay? So S15 is A was 6 times 1.05 times 1 minus R, which is 1.05 to the power 15 over 1.05 like so, okay? And this, we can now, this is the sum for the 5 to 20th kilometer. We add the first 4 kilometers, which is 24, and this will give me the overall time that it takes for her to complete the marathon. So using the formulas, it's not very difficult. It's understanding what our A term here, because it's slightly different to what you'd think it would be, right? Some students do get mixed up and use A as 6, and that will be a mistake, right? So it's to just make sure you understand when does the geometric sequence start. That's really the main part of like A-level maths, is understanding how to apply your knowledge, right? Because understanding your knowledge is not very difficult. Like we just learned how to do arithmetic and geometric really quickly, right? It's just making sure you understand what our A term is and how we go ahead and apply it to the question and go ahead and try and find the right answer. Okay. We can do another example here. So once again, it's another geometric example. So we have a trading company made a profit of £50,000 in 2006. That's year number 1. A model for future trading predicts that the profits will increase year by year in a geometric sequence with a common ratio of R which is greater than 1. The model therefore predicts that in 2007, year 2, a profit of 50,000 times R will be made. Write down an expression for a predicted profit in year N, okay? Right, so in the first value A obviously is 50,000, and then the common ratio R is just R, right? So UN just simply will be 50,000. It's a 1-mark question, so it's R to the power of N minus 1. This should be fairly simple for us right now. Okay. The model predicts that in year N, the profit will exceed £200,000. Show that N is larger than log 4 over log R plus 1. So they're saying that in year N, Sn is going to be larger than 20,000. So we're going to have to use the summation equation. So we can say that Sn, which is going to be equal to A, 50,000, times 1 minus R to the power of N over 1 minus R. And this is going to be larger than 200,000, like so. Now it's just a matter of rearranging it, okay? So if we go ahead and do rearrange it, what do we get here? We have we have 1 minus R to the power of N, 1 minus R, going to be greater than 4. I think they've missed out a couple of questions, okay? So I think this, I think we didn't write out the next part. So I think we'll just skip ahead for this one. All right, so we've learned now the arithmetic and geometric sequence and series. We're now going to be looking at sigma notation. And so a sigma notation will look something like this. It's actually a Greek symbol, okay? And it just means the sum. So what we're doing is summing from, you see here R, is 1. Normally it starts with 1. It doesn't start with 1 all the time, but I'll show you how to deal with it. We're summing the first term all the way up to the nth term. So it's basically giving you the limits of the terms you need to sum up. So this one here, basically we're summing up from the first term r is 1 to the 5th term, and this here will define each term within the sequence. Now, because we've learned the arithmetic and geometric series, most of these summation formulas will be based upon the arithmetic and geometric series, so you can use the formulas that we've learned. It's just a matter of identifying which one it's going to be. And the way we do identify is all based upon where the r value is, okay? So if the r is multiplying certain constant values within the sequence, then it's going to be an arithmetic series, okay? So this one here is going to be an arithmetic series. If the r is being raised to the power of the number, for example, this one is going to be a geometric series. So we should use the geometric equations. That's how you go ahead and identify which one's which, okay? So if you look at these 4 examples here, this one here, the arithmetic, this will be arithmetic, right? Because r is multiplied to the term. This one here, r is the power. So this will be a geometric example. This one here, r is once again multiplied, so it will be an arithmetic. And this one here, r has been raised to the power, so it's once again going to be a geometric. So we know which one's which. Now we know which one's which, we also have to identify the a values and the appropriate d or r values, okay? So the way we go about finding the a value is just simply plug it in, okay? So what you want to do is plug in r is 1 to this series. And if you plug in r is 1, we get 7 minus 2, which is going to be 5. This is going to be your a value, your initial term. Same thing for all of these, just simply plug in a is 1 or r is 1. So if you plug in r is 1 to here, so it's going to be 3 times 4 to the power of 1, which is just going to be 12. And once again, this is equal to a like this. And then for this one here, just plug in r as 1. So 2 times 1 minus 8. And what do we get? We get minus 6. This would be a. And finally, just plug in r as 1 to here, and you get a as minus 7 over 3, like so. Okay, so that's how you go ahead and find the a value. Now, we also need to find the common difference and the common ratios for each one. So once again, for this first one, it's a arithmetic one. The common difference is basically the term multiplied to r. So in this case, we are multiplying by minus 2. So the common difference will be negative 2, like so. For this case here, we're multiplying by 2. So the common difference will be just 2, like this. For the common ratio, simply what's the base of the exponent? So in this case here, the base was 4. You can see here is 4, right? So the common ratio will be 4. And this one here, the base is going to be 1 minus 1 over 3, like so. Okay. All right, so let's try and do, well, actually, if we go back to the previous example, let's actually try and solve some of these questions, okay? So let's try and just solve this one here. So we have the sum. We know it's an arithmetic sequence, right? So we can use the arithmetic equation, sum from S1 to 20, so the first 20 terms. And that's going to be n over 2, so 20 over 2 times 2a. Remember a, when we plugged it in, is going to be 5 times 5 plus n minus 1, 20 minus 1 times the common difference, which is minus 2, like this. And this will give me the sum for the first 20 values. Okay, so if I plug into calculator, I get minus 280, like so. So it's very simple, right? Now, the difficulty is, as I said, it doesn't always have to start with r is 1, okay? There are cases when it doesn't start with r is 1. So, for example, if I ask you to find the same formula, 7 minus 2r, up to the 20th term once again, but from r is, let's say, 4, like this, okay? Now, whenever it doesn't start with r is 1, this plugging into this summation formula we learned earlier is not going to give you the correct answer, okay? So because it only works for when it does start with r is 1. So we need to manipulate this slightly. So what I'm going to do is I'm going to say this is going to be equal to the sum of 7 minus 2r from r is 1 to 20. And I'm going to subtract certain terms, okay? Right, I'm just going to simply write out some of these terms, okay? So the first term, remember, was 5. So the next term will be, if you subtract 2, so 3, 1, minus 3, and so on. Minus 5, and so on, okay? Right, so maybe I should write it a bit clearer for you guys. Right, so the first term, remember, was 5, and we're subtracting by 2, so 3 plus 1 plus minus 1 plus minus 3 plus minus 5, and so on, okay? Right, until the 20th term. Now, if it starts from RS4, what they're asking for is from the 4th term to the 20th term. So essentially, they're asking for 1, 2, 3, these values here, okay? So we don't want the first 3 values, the 5, 3, and 1. So what we have to do is actually subtract, because this minus 280 was from 1 to 20, right? We actually have to subtract the 1 to 3 terms. So what we do here is we subtract from RS1 to 3 of the same equation, 7 minus 2r, like this. This is very important you guys know how to do this, okay? So whenever it doesn't start with RS1, in this case here, all you have to do is subtract from RS1 to, in this if you take this as n minus 1. So if this is 4, it'll be 3. If this was from RS10 to 20, this here will subtract from 1 to 9. Okay, so just make sure you understand that you have to subtract if it does not start from RS1. And now I just do minus 280 subtracting this term here, which we can find once again if you plug it into the summation equation, or you can just simply add these up if you wanted to. All right, so let's look at this one here. So we find the value of from R20 to infinity of this equation here, or this formula, 200 times 1 over 4 to the power of R. So Tammei Mango, thank you for the comment. If you do have any questions, just do comment and I'll try and answer them if you do have any questions regarding what we're learning now. All right, so yeah, so back to this. Once again, first things first, let's identify, is it an arithmetic series or a geometric series? So we know that the R is in the power position, so it's going to be a geometric series. And so our R value is just going to be the base of that, so it's going to be 1 over 4. That's a common ratio. Now, our A term, the first term, just simply plug R is 1 into here. So it's going to be 200 times 1 over 4 to the power of 1, which is just going to be equal to 50. So we found our A term and our R term. And it's from R is 20 to infinity. So there's 2 things to note. It's infinity, right? So we should be using the sum to infinity equation. Sum to infinity. However, if we use the sum to infinity equation, we get from the first term all the way to the infinity term, right? And we don't want these terms here. So we should manipulate it a bit. So if I do manipulate it, it's going to be 200 times 1 over 4 to the power of R, from R is 1 to infinity. And then we have to subtract from that the same 200 times 1 over 4 to the power of R, from R is 1, not including the 20 terms, so R is 1 all the way up to 19, like this. Okay, so this is an example of what we did before, right? Because it doesn't start with R is 1. And now we've got 2, so we just simply find each one separately. Okay, so this one here, just simply using the summation formula, our A is not going to be careful, it's not 200, right? We found it earlier. A is 50, right? So 50 over 1 minus a quarter, a common ratio. Subtracting. Now this here, we should use the sum equation, not the sum to infinity equation. So 50 times 1 minus 1 over 4 to the power of 19 over 1 minus 1 over 4. I'm not going to work this out, but you can just plug into calculator. But this is how you go ahead and basically apply or use the geometric and arithmetic sequences series to find sigma notation equations. Yeah, this is just some more examples. I don't think we have to like go through this, but in this case here, R is 2, right? So it's going to be, so R is next to the value of 5. So it's going to be an arithmetic term with a common difference of 5. If you plug in R as 1 into here, you get a first value A as 9 over 2. Other things, so you should use these arithmetic series formula. Other things to note is that R does not start off with 1, remember? So you have to subtract from here 1 to 8. Okay, that's just an example which maybe you guys can try on your own. Okay, so as I said, most of the sigma notations will be based upon the arithmetic and geometric sequences, okay? However, there are certain sigma notation questions like this, which cannot be found by either two concepts, and it's more a logical mathematical deduction kind of exercise. So let's look at here. We have n is 2, from n is 2 to infinity, and this here, I want to show that it's equal to 9 over 8. At first glance, it doesn't really seem very obvious, right? So we don't really know whether it's an arithmetic term or a geometric series. So in this case, what I'd advise you to do is basically plug in certain values of n, starting off with the first value. So let's plug in n is 2. If you do plug in n is 2, we get 3 over 4 squared cos 360. 180 times 2, 360, right? And that's just going to be, if you look at the cos diagram, cos 360, that's just going to be 1. So I'm going to times it by 1. The second term will be 3 over 4 cubed times by cos 180 times 3 is going to be 540, and that's going to be minus 1, like this. So times in minus 1. The next term, 3 over 4 to the power 4, and then if you do the same thing, that's actually going to be times 1 again. So the reason why we did this is now you can see, you can slightly visualize what's happening, right? We get certain terms, and you can see that first of all, the cos terms will be 1, minus 1, 1, minus 1, interchange like that. And we're actually multiplying by the same value of 3 over, sorry, right here. We're actually multiplying the same value of 3 over 4. In fact, we're multiplying by minus 3 over 4 each term. That's how we can compensate for the cos terms changing from plus and minus 1. So now, this, because we're multiplying by the same term, is now changed into a geometric series, with our a term being this first term here. So a is going to be 3 over 4, so 9 over 16. And our r, common ratio, is going to be minus 3 over 4, like this. So from this initial sigma notation question, we now just found out, or changed it up into, or found out it's actually a arithmetic or geometric series. And so if it's from infinity to infinity, right? So I just simply have to do sum to infinity, 9 over 16, 1 minus 3 over 4, which is plus, and this turns out to be what they want us to do, 9 over 28. So at first glance, it does look very difficult, but my advice is just simply plug in n values from the smallest n, and you should hopefully try and see a pattern. This is another example of trying to see a pattern, right? So once again, we don't know whether it's an arithmetric or geometric, right? So as I said, just plug in n values. So let's go ahead and plug in n is 1. So if I do that, it's going to be log n plus 1 is 3 over 2 to the base 5. With summing it plus, if I plug n in 2, log, it's going to be 4 over 3, same base, 5. Let's do one more. So log 5 over 4, base 5, and so on. I'm also going to plug in the last two values as well. So let's plug in log, this up to the 48th term. So let's go ahead and plug in the 47th term. So it's going to be log, if I plug in 47, it's going to be 49 over 48, base 5, plus the last term will be log 50 over 49, like to the base 5, like so. Now, when we did this, it doesn't really look like either of the arithmetic or geometric series, right? But in this case, what we can use is the log rules. Because we're adding it, remember the log rules means we can just multiply each of these terms here, right? Just multiply each of these terms within the log bracket. And as you can see, if you multiply, you'll see that this 3 and this 3 will actually cancel out. So they'll cancel. So with this 4 and this 4, and this 5 and this 5, and this 49 and this 49, and so this 48. And essentially what you're left with is log 5, go to the base 5, this 50 here, 50, over the initial 2 here. So essentially what we get is log 25 to the base 5, which is just essentially 2. Okay, so that's how we get this one. As I said, this case is neither geometric or arithmetic. It's just simply plugging in n values and trying to use mathematical deduction to answer these types of questions. And the final part of the A-level course, which does in terms of series, is looking at recurrence relations. And the recurrence relation is when each term of a sequence is a function of the previous term, like here. You might have seen that, like, for example, un plus 1 is equal to 2un plus 1. This is a recurrence formula, because it tells us, if we know the nth term, it tells us the n plus 1th term, okay? And they'll give you like the first term. So they'll say like u1 is 2, for example. And they'll ask you find u2, u3, and so on. And what you basically have to do is, if I want to find u2, I just do 2 times u1 plus 1. u1 is 2, right? So it's going to be 2 times 2 plus 1. This is just 5. That's going to be our u2, like this. And then you just plug in the next one to get u3, and so on and so on. This recurrence relation part of the course is not very difficult whatsoever. It's just making sure you plug in the right values. The thing that is yet to be aware of is that you have to know what a increasing or decreasing or even periodic sequence is. So an increasing series or formula, recurrence relation, is when the terms increase in values as we go along. So an example would be like, let's just go 2, 4, 8, 16, 32, and so on. This will be known as an increasing series or sequence. A decreasing one is therefore the opposite. It just goes down in value, okay? So like -1, -4, -7, -10, -13. This is known as a decreasing sequence. The last one is a periodic one. So a periodic one is if the terms repeat in a cycle. What we mean by that is, for example, if I said 1, 4, 7, 1, 4, 7, 1, 4, 7, for example, like this, right? You can see the numbers will repeat, so we know the next terms. This is known as a periodic one. And the only thing we need to know about this one is that it has something called an order or a period. It just means how many terms does it repeat, or after how many terms does it repeat? Well, it has 3 terms within it, so in this case, the order will be 3, okay? Basically, just count how many terms there are within each period before it repeats, and that will be the order of the sequence. Okay, so yeah, so that's really all there is to the series part of this A-level course or A-level live course. Do let us know what you want to do or what you want to go through next week. We'll be doing lives every Saturday at the same time, 2 p.m. UK time. So I'll hopefully see you next week as well.